Yeah, I can see your screen.
Yeah.
Okay, go ahead.
Yeah. Hello everyone. My name is Jinting, and I will give our talk about integrating ADTs in KeY and their application to history-based reasoning. This is a cooperative work with Hans-Dieter Hiep, Frank de Boer, and Stijn de Gouw. First, I will give a briefly introduce of our toys, the state-of-the-art theory prover KeY. The reason why we choose this is because this is the only tool that allowed us to load related Java code, and this tool is tolerant to be the verification of Java program. The annotation languages of KeY is GL, and the inner logic is the Java DL. This is the reason why we do this. Our ambition is to give specification and verification of the whole Java collection framework. The first things we choose to verify is a linked list. So we give a paper of verifying OpenJDK's linked list using KeY. And then we give an extended paper about tutorial on verifying linked list using KeY. In this tutorial paper, we show the tutorial on how to use KeY, and we give a details to verify the add and remove method. In our main paper verifying OpenJDK linked list using KeY, we find an integer overflow box, and we give a specification and verification of the implementation of linked list. And actually, we skip some method in linked list, like the add-all, because the add-all takes an interface and a parameter. So we skip this in this paper, but we want to go ahead. So we give a paper to solve how to give specification and verification of the add-all method. We give a paper about history-based specification and verification of Java collection using KeY. But when we finish this paper, we find that we still cannot verify some complex client-side examples. So now we give us our paper about integrating ADTs in KeY and their application to history-based reasoning. Let's begin the first part, how to integrating ADTs in KeY. What is ADTs? ADT is the abstract data type. The ADTs is mostly used to reason about data on higher level of abstraction. But the problems come. The tool we use, KeY, has no direct support for the user-defined ADTs. Actually, KeY has some inner-defined ADTs, but it's not allowed us to define our own ADTs. So we gave the solution for our previous work. We model ADTs using Java class, but for our now work, we use user-defined source and customer-proof rules in KeY theory prover. For the previous work, the advantage is that we can define at level of programming languages. That means that the functions are computable and available in Java. And in this approach, we only need to use no Java and GML. The disadvantage is that we need to lifting our two specific languages, especially for the peer functions. And because we use a Java class, so we need to solve lots of verification overhead, like we want to show the functional determinant, and heap dependencies. But for our now work, we use user-defined source and customer-proof rules in KeY. The advantages for this approach is that we can declare specifications, no programming needed because we don't use Java class. We directly use specification in our method, and we have no interference by Java program execution. The disadvantage is that we not only need to know Java and GML, we need to familiar with the proof rule and Java DL when we use the user-defined ADTs. And it's a possible inconsistency because the ADT is defined by us. So it may cause inconsistency. But now we give an update of our approach. We talk about integrating ADTs in KeY approach. The first step we use is we introduce a new toy, the Isabelle. Actually, Isabelle is a very good toy because it allowed us to use formal languages to express mathematical formulas, and it's proving formulas in a logical way. The most advantage is that in Isabelle, it don't have any state changes. In KeY, the KeY is a state-based theory prover, but in Isabelle, it don't have any state change. And the first step is we use in Isabel, we define the data type and abstract property. For example, we define the data type alpha option. We can give the option type is either null or some object. The second step is we translate data type and abstract property into the source and the functional symbols. For the example we gave, we translate the source to option, and the function we can give it as either the sum object or none. The third step is we use the functional symbols in Gmail specification, and in KeY serial prover is provide a escaped head /dl to directly to the function. We can give a precondition, for example, like we can say that the DL sum object is equal to object O. The first step is we use KeY to generate proof application and find what serial is needed. And for the next step is we prove the series in Isabel. For example, if we want to prove that if some object O1 to some object O2, the by implementation of O1 to O2, we can directly prove it in Isabel because we have the definition in Isabel. The next step is we translate the series of Isabel to proof rules in KeY. For the example we gave, we can translate to the template in KeY, like we find some object O1 to some object O2. We can directly replace with O1 to O2 in KeY serial prover. For the next step, we import these proof rules in KeY serial prover. And actually, we cannot do all the things at beginning. So we will redo the step 4 to step 7 and until finish the whole proof. While our approach is great, the first is because our approach is very lazy. We only need to verify the series we need when we find we need it. And because we prove the series in Isabel, so we can say that our approach is consistency and the translate is soundness. Next, I will come to the second part, the application to history-based reasoning. The problems come how to reason about Java interface in KeY. Not like the Java class, there's no concrete state available in KeY serial prover, but actually KeY is state-based verifier. The solution we give is using history. What is history? History is a sequence of events, and it keeps track of all method calls and returns in a history, and every object has its own histories. This is our history-based reasoning approach. The first step, we will record method invocation on an interface using a history. For example, we can say X is an interface and O is object. If we want to add an object in interface X, if the return value is true, we can say that it's add event. The parameter is the object O, and the return value true. We can say that this is an event in a history. Next, we will define abstract property of the history. Here, we use a multiset to give a modular the context of the collection. For the example we gave, we can say that the multiset will be the old history unions of the new object O after we added the add event. And the third step is specify object behavior in terms of its abstract property. For the example we gave, if in the boolean add method in the interface collection, we can say that the multiset will add 1 if the result returns true. Otherwise, if the result is false or the object O prime not equal to O, the multiset will remain the same. But the problem is that we have no built-in support for histories in KeY. This history here is our own history, and we give the solution for the previous work is we model histories using Java class. But now we can introduce ADTs in our work. Here we give a very simple example of the client-side example of the add. If we want to add the object Y into collection X, if the return value is true, for our previous approach, we model histories using Java class. So we say that history.multiset add 1. And here multiset is a Java class. But for our now approach, we use the ADTs, and the multiset become a functional symbols, and the multiset actually defined in Isabel. And we can see that /dl multi-set here. And this x.history is just associate history to interface in the instance, and /dl is a escaped attach. For the previous work, we use Java object to encode histories, and we use Java method to define functions. Actually, here we need the total verification effort is 78 minutes because we need to verify the peer method multi-set. And this take our 72 minutes and 6 minutes for such a simple example. But for our ADTs, we don't need to care about the multi-set because it's just a definition in Isabelle. And we follow the ADT approach. And the example in our ADTs is automatic. So the whole verification effort is automatic. Because our method is improve a lot of improve, so we want to verify the more advanced client. Because the time limit here, I gave a previous of other example we verified. We verified iterating over the elements of the collection. We want to show the iterator and its owning collection, the relationship between the iterator and its owning collection. And because this example, we need to have lots of peer functions like size, iterator validated, iterator has next to show the relationship. So this take lots of effort. It takes more than 8 hours to finish the whole proof. But for our ADTs approach, we don't need to care about these peer functions, and the client side example is automatic in KeY serial prover. And next example is a modifying iterator. This example want to show that if we want to remove from iterator, it's also removed from collection. We want to show that every object has its own collection, its own histories. And we want to show that in this example, Isabelle can use to drive non-trivial properties. And next example is adding elements of one collection to another. The before examples only talk about one collection. Here we want to show that we can operate on 2 collections. And the most important thing is that is with specification of add-all method in these examples. The final example is the most complex one. We're comparing 2 collections. We want to show that whether these 2 collections is equal or not. For the third one and the fourth one examples, the first one takes 75 minutes, and the last one is take 75 minutes. But we not verify this complex example in previous approach, and we think it will take several days if we do the whole approach. And the main contribution of our work is we're integrating ADTs in KeY serial prover, and we use Isabelle serial prover as an interactive backend, and we translate Isabelle serial to user-defined proof rules in KeY. And actually, we guarantees our approach is consistency. And next, we gave several client-side example to reason about Java collection interface using history. And the most important things, we improve a lot of proof efforts. For our future work, we will continue with the specification and verification of Java collection framework. Here, we only talk about add-all method, and we will continue do on the remove all, continue and retain all, and extra. And we will also do on the collection. We not only do on collection, we also want to do on map, set, list, and extra. And we want to generate history-based refinement theory. This is also the work we now do. We want to verify that a collection can implement a history-based interface. For example, like linked list we do is actually implement from the collection, and we want to generate the refinement theory before it in it. So that is my whole talk. Thank you for listening.
Thank you for the talk. Are there any questions from the audience? I don't see any questions yet. Maybe while some of you think of a question, I also have a question. With some of these cases with the experiments, you didn't give the times for the automatic. Is that because it's basically instantaneous, or can you say anything about that?
The automatic means that we the proof doing in Isabel is automatic, and also the client-side example doing in KeY serial prover is automatic. So
But
that's what it means about.
Can you say anything about the runtime? How long does it take to do that proof?
The runtime?
Yeah.
Maybe it don't take too much. Maybe 10 seconds or 10 seconds is enough for automatic in KeY. And what we mean auto is we don't need to do anything by ourselves. We just push the button, or it will be done, hold down by KeY.
Yeah, sure. And when you talk about the time it used to take, then of course you assume that the user is fully versed in the techniques.
No, what we mean is who is very familiar with the KeY serial prover and KeY serial prover.
Yeah, okay. Yeah, that's what I mean. Okay. And in terms of future work, is there so you mentioned that you want to verify more collections. Is your technique limited in some way, or maybe you cannot foresee that yet, but where you think, well, if I want to verify these, I still have to extend my technique for that, or?
Yeah, we don't know. Actually, we just want to keep our work on the verifying collection framework. And actually, we don't know what difficult we will meet, but we have the ambition that we want to verify it.
Yeah, okay. If there are no, I don't see any questions from the